Hello everyone and welcome to our sessions on digital heritage inspection and survey, which are kindly funded by Historic England. This is a programme of 10 sessions for learners of different experiences and backgrounds to find out more about how digital models and digital twins are being used in the heritage sector. There's a WhatsApp group where the learners can co-mentor and share resources too. My name is Linda Jubb and I'm your host today. I'm a Chartered Building Surveyor and Fellow of the Royal Institution of Chartered Surveyors. Our practice, Jubb Clues, specialises in the survey and repair of historic buildings. My co-host today is Kira Greenwood from Christians, the survey company.
So hello everyone, it's a pleasure to be here to talk all about surveying today. I'm Kira and I've been part of the surveying industry for over 8 years. I started my career straight after earning my degree in interior design at UCLan and I joined Christians as a CAD technician. Today I'm the Director of Operations responsible for managing projects, conducting site visits and coordinating access and ensuring quality control across all our work. I've conducted site surveys, created CAD drawings, modelled buildings in Revit, and even appeared on Digging for Britain, where I surveyed an underground mine which was recently discovered by a gardener. This demonstrates the diverse and fascinating opportunities that surveying offers. So a little bit about Christians is that we started as an arboricultural surveying firm, specialising in tree surveys and consulting. Over time, we've expanded from topographical surveying, and now we were also early adopters of laser scanning technology, which set us apart in the industry. We pride ourselves on staying ahead of the curve with innovative surveying techniques, particularly for unique and historical buildings. Our services include producing 2D drawings, 3D Revit models and photogrammetry models, each tailored to meet our clients' needs with precision and accuracy. This is just a brief overview of what we do, but I welcome you to check out our website to see all the services that we offer. So I'm excited to kick off this informative 6-week course and I'll be leading both of the technological sessions. Today I'm here to talk about the digital models within the heritage sector. I'll talk about the technology behind producing a digital model, from collecting the data to processing the information, and the many ways that these can be of use within all sectors, but specifically heritage. Digital models. So what are we trying to create? So digital models allow us to recreate physical structures, buildings or landscapes in a virtual environment. By using advanced tools like laser scanning, photogrammetry or 3D modelling software, we can capture the details, dimensions and features of these real-world elements with incredible accuracy. The technology is essential for industries like architecture, conservation and design, as it enables seamless reviewing, planning and collaboration, whether you're producing 2D plans, 3D models or photorealistic visualizations. Digital models serve as the foundation for informed decision-making and effective project execution. In short, digital models bring the physical world into a digital format, giving us the ability to explore, measure and interact with objects without needing to be on site. I'd be interested to see how many of you have seen or even used one of these models in your careers or studies. I think we'll do a poll later on just to find out. So, digital models. Digital models can be created using a variety of data sources and methods, each with distinct characteristics and applications. The primary types of digital models include point clouds, mesh models, and photogrammetry models. These can also be merged to create a hybrid model. Point clouds are made of many individual points in a 3D space, usually created with laser scanners. They're accurate for capturing shapes and sizes, but don't show close-up surface details. They're usually used in surveying, architecture, and engineering. Mesh models use polygons, which are often triangles, to form the surface of an object. These models are detailed and realistic, making them ideal use for video games, movies, and 3D printing. Photogrammetry creates 3D models from overlapping photos taken from different angles. This method is cost-effective and visually realistic, often used in archaeology, film, and visual tours, but may not be as accurate as other methods. And a hybrid model is a mix of point clouds, meshes, and photogrammetry to get the best of all methods. They are used when both accuracy and detailed visuals are important, like in construction and historic building modelling. These models are also known as digital twins. So in part 1 of this course, you'll learn about what a digital model is, gaining insight into visual representations of real-world objects and environments, how the data is captured, learning how tools and techniques like photogrammetry and laser scanning are used to collect the data, how the data becomes models, so discovering how raw data is processed into actionable 3D models, and how the models are used, understanding how viewing and applying models can aid in better decisions and workflows. Creation of a digital model involves a series of precise steps that combine survey control, laser scanning, and photogrammetry to produce an accurate and detailed 3D representation. We'll visit each of the 3 steps to discuss the ways in which we collect the data and then combine them to form a digital twin. Part 1. So part 1 is the survey control, establishing a precise reference framework using ground control points, or GPS, to ensure that all captured data aligns accurately in consistent coordinate systems. The next step is laser scanning. By centering the laser scanning around the control, we ensure that the project is aligned with precise coordinates. Once the laser scanning is completed and processed, the resulting model serves as a foundation for wrapping the photogrammetry, guaranteeing both accuracy and proper scale. Part 3 is the addition of photogrammetry, which is the process of capturing overlapping photos from multiple angles to create accurate, realistic, and measurable 3D models, which are then integrated with existing data to produce a digital twin. These stages work together to create a high-precision, detailed digital twin model suitable for analysis and decision-making. So let's dive into part 1, the survey control. To create an accurate control network around a building, targets are used to establish reference points and close a traverse. This involves setting up visible markers, surveying distances and angles with tools like total stations or GNSS, and adjusting the measurements to form a closed loop. By ensuring minimal errors, a precise control network is created, which serves as the foundation for accurate data capture and georeferencing, resulting in a reliable 3D digital twin model. At this stage, you don't need to understand the detailed closing loop calculations, but it's crucial that any errors are minimal to ensure the accuracy of the control network. You'll see our surveyor Sean in this video setting up his total station over a nail, ready to complete a traverse loop. The nail serves as a fixed reference point and the total station is aligned with it using the optical sight. After confirming the station is level, the known coordinates for the nail may be input into the total station, allowing for accurate measurement and data collection. So how the survey goes together and making sure that it's in the right place. So a traverse is performed using the GPS, total station and precise levels to establish a control network. The GPS establishes the positioning of the traverse and provides accurate coordinates for control points, especially in large areas or where precise georeferencing is required. The GPS receivers are set up at key points, collecting data on latitude, longitude, and elevation to record positions with high accuracy using satellite signals. The total station measures the horizontal and vertical angles, as well as distances between control points, ensuring accurate geometric relationships within the traverse. The surveyor sets up the total station at each nail's setup, just like the video of Sean in the previous slide, measuring angles and distances to other points, which are then used to calculate the precise precisions of the nails. Nails are permanent reference points used in control network for accurate surveying. Now let's discuss how the targets are used to align and geolocate laser scan data for precise 3D modelling. Survey control targets are an essential part of laser scanning and 3D surveying, providing reference points to ensure accurate data alignment and registration across scans. These targets are typically highly visible and come in various forms such as checkerboards, spheres, or prisms, and are strategically placed in the environment. Once you're aware of what these targets look like, you'll start noticing them everywhere, whether it's a checkerboard sticker on a wall, a reflective sphere mounted on a tripod, or a prism tucked into a corner. These targets are quietly helping surveyors achieve precise control over their measurements. So next time you walk through a town, a city, or just down the street near where you live, just take a closer look and you might just spot these little markers doing the crucial job in the background. If you spot one that you think maybe a surveyor is using, send a picture of it in the WhatsApp group. So the key benefits and takeaways for the survey control are its accurate placement positions the project in the correct location using OS or local coordinates. Integrated elements allow different survey elements to be joined into a cohesive framework, and it ensures accuracy, providing a basis for required precision with error adjustments. It's expandable, allowing future work to be seamlessly added into the existing network, and it enables comparative analysis for future measurements to be compared with previous data for monitoring changes.
Okay, so I've launched a poll here, which is just to find out just kind of like how much you're using this. It's fine if you're using them not at all, you've come to the right place. If you're using them all the time, you've still come to the right place because you might not be using them in heritage projects. And we really want you on our team working over here in historic environments. And let's share these results. Okay, so we've got 2 people who are using these every day. Was that you, Kira?
No, it wasn't actually. I was
at least you're one of the people who didn't vote. So the people out there are using these models every day, and a good proportion are using them every week. Every now and then, I think I would probably be between every week and every now and then if I'd voted. I didn't get a vote because I'm the host. 33% are not really using them and 26% not at all. So that's nearly half of our audience here today are not using digital models and not really using them day to day. I'm delighted by that figure actually, because that means that there is an opportunity through this program of sessions for people to learn about it and get their confidence. And I really hope that if we were to take the same poll with the same audience this time next year, it might be a bit higher. Right then, Kira, are you ready for another session? Is everybody suitably relaxed and we can go into the next few slides? Okay, back to you.
So let's discuss part 2 of the digital twin, the laser scanning technology. Laser scanning is a cutting-edge technology used to capture detailed 3-dimensional information about the shape, size, and spatial relationships of objects and environments. Using laser beams, this process generates accurate and high-resolution 3D models by measuring distances and recording millions of data points in a fraction of a second. Applications can include architecture and construction, engineering and manufacturing, surveying and mapping, and archaeology and cultural heritage preservation. Each component of a laser scanner plays a crucial role in creating accurate and detailed models. Let's take a look at each part and the role it plays. The deflecting mirror redirects the laser beam in different directions, enabling the scanner to cover a wide area. The GNSS antenna, which stands for Global Navigation Satellite System, provides accurate geospatial positioning by receiving signals from satellites to determine the scanner's location. The angle measuring system tracks the orientation of the scanner, ensuring precise alignment of the laser's direction. The HDR imaging camera captures high dynamic range images that enhance visual data, especially in environments with varying light conditions. The IMU unit, standing for Internal Measurement Unit, monitors the scanner's movement and orientation, ensuring that the data's accuracy during mobile scanning is operating. The Wi-Fi antenna facilitates wireless communication, allowing real-time data transfer to external devices like laptops or tablets. The Viz camera captures high-resolution images of the scanned area, which are used for texture mapping in 3D models. The distance measuring system calculates the distance to objects by measuring the time it takes for a laser beam to reflect back to the scanner. Two components that are not listed but are very important to the process are the mounting system, ensuring that the scanner is securely positioned, whether it's handheld, tripod mounted, or drone mounted, critical for stability and precision during the scanning. The user interface, could be a display or an app, allows operations to configure settings, monitor scanning process, and view basic results in real time. Often includes touchscreens or companion apps for smartphones or tablets. Together, all these components enable laser scanners to capture accurate spatial data, create 3D models, and provide detailed visual documentation. How the scanner works. The scanner is typically mounted on a tripod for a stable, elevated position, ensuring accurate data capture. The mirror in the scan head rotates vertically at high speed, emitting and capturing laser beams across a wide range. Simultaneously, the scanner body rotates slowly horizontally to cover the surrounding area comprehensively. Users can adjust the settings such as density, quality, and range depending on the project requirements. Different makes and models offer varying capabilities for flexibility. The scanner needs a clear line of sight to the objects being scanned, as it's not an X-ray machine, so obstacles can block its effectiveness. This is the process of collecting millions of 3D points, which are then processed together to form a point cloud back in the office. So let's take a look at an example of a point cloud. A point cloud is a collection of million or even billions of points in a 3D space that represent the external surface of objects or environments. These points are captured by laser scanners or other 3D imaging devices, which each point is assigned an X, a Y, and a Z coordinate to define its precise location in space. In some cases, additional information such as colour, RGB values, or intensity, reflectivity of the laser beam is also recorded. Point clouds appear as dense clusters of dots that form the shape of the scanned object or area, offering incredible precision and detail. They are widely used in applications such as 3D modelling, engineering design, architectural planning, visual reality, and cultural heritage preservation. Despite the versatility, point clouds require processing to convert them into more usable formats like meshes or CAD models to allow for detailed analysis or implementation in projects. It's important to note that laser scanners require a clear line of sight to the surface being scanned, which can result in data gaps in hidden areas. Additionally, high-density point clouds generate large files that can be challenging to work with specialist computers. However, the level of detail and accuracy provided by point clouds makes them an essential tool for capturing and recreating real-world environments in a digital form. So there are both pros and cons to laser scan technology. Let's summarise the pros and cons, and then we can see how the laser scanning can be a powerful tool with incredible benefits, but we do have to consider the specific requirements and constraints of a project before the implementation of this technology. So its pros can include high accuracy and precision, capturing highly detailed measurements with millimetre level accuracy, making it ideal for application requiring precision. Speed and efficiency, quickly collects millions of data points, reducing the time required for manual measurements. Comprehensive data capture, providing a full 3D representation of objects or environments, enabling in-depth analysis and visualization. Versatility, applicable across various industries, including architecture, engineering, manufacturing, and construction. It's non-invasive, meaning that it safely captures data from a distance without physically touching or altering the scanned object. It offers remote scanning capability, so you can reach across areas in challenging environments such as hazardous sites, which you then don't need to enter. Its enhanced safety reduces the need for personnel to enter the potentially dangerous locations for to collect the measurements. And its integration with other technologies works seamlessly with GPS, cameras, and thermal imaging for additional data layers and enriched outputs. As well as these pros, it does come with a few cons, and one of them being high cost. It could be an initial investment, which can be expensive, but makes it less accessible for smaller projects or organisations. Its line of sight limitation requires a clear path to the scanned object. Hidden or obstructed areas may result in incomplete data. The point cloud is a raw file and it must be processed into usable formats like CAD models or meshes, requiring time, expertise, and powerful computing resources. Finding a company to provide a survey is the best solution to overcome this, as they'll already be covering these costs. The high-density data can generate large files that demand significant storage space and computing power to handle, and also survey companies will store your data for a minimum period of time, meaning you don't need to have a large storage system. The environmental sensitivity performance could be affected by environmental conditions like bright sunlight, dust, or reflective surfaces. Laser scanning can be an invaluable tool when utilised in the right professions. So some key benefit takeaways from the uses of laser scanning are that it's efficient and reliable, it's data-driven decision-making, it's ideal for complex projects, it's a comprehensive 3D representation of the real-life object, and it's also non-contact and safe data way to capture. Hey, Linda?
Thank you very much. I'm here, I'm back. I hope this is helpful for people to go in these little sprints where we're taking on lots of sort of quite dense information. And I do realise that this is a sort of interdisciplinary group. So some people in the room here, I think I'm going to do a hands up now. Hands up if you're working in geospatial, because there were quite a few people from practices like Christian's who've come along today, for whom this will be bread and butter work. They'll be doing it all the time. Can I just have a show of hands for those people? So, oh, there's Lydia. Hello, Lydia from Circle. You're using this all the time then. So hopefully that was useful précis for you.
Yes, thank you.
There it is. Hi, Lydia. And the people who are less familiar with this tech, how are you getting on? Gordon, hello. How are you getting on, Gordon?
Oh, yeah. Can I ask a quick question about calibration? How often, what's involved, or it's not required? Thanks.
Not required. Usually it comes with whatever technology you're using, whether it's a total station, a laser scanner, their manufacturer warranties or specifications should tell you when calibration is required, and they'll either get in touch with you or they'll they'll drop you an email regularly to make sure that things are calibrated. You can book in services for equipment. What equipment is it that you're using?
Actually, I don't know the answer to that question. Various scanners, some of them are mobile and some of them are static. But it was really in terms of the person that owns the equipment, as opposed to maybe Historic England with a specification that expects you to have the calibration. It's kind of how often do you do that? Some big projects, they sort of expect you to come with a very recent certificate to validate it. Others, maybe they're less diligent.
Yeah, right. Some people won't specify it because they won't really know the importance of it, but other people do, and they say that it has to be a recent calibration. Things like having the laser scanners in the back of a van or the boot of a car can actually throw out the calibration if it's been in a bump or an accident. It's quite important for the equipment to be calibrated. It can throw off if you're doing a scan in a position, your meeting point of the scan can not line up due to calibration. So it can cause all sorts of issues, which then would run into the registration of the point cloud. So I would highly recommend calibration. Checking what your manufacturer says for that equipment, how often they would recommend it. But even just like on a personal note, once a year at a minimum.
That was a great question, Gordon. And
Thanks.
I think that later in the programme, we're going to look at some of the survey specifications and in particular how people use them, because as Kira's pointed out, this is about the relationship between the surveyor or the survey firm and the client, making sure that clients' needs are met, but also for surveyors ourselves in terms of our professional discipline, is making sure that error control is built into every stage of the process. And as Kira says, that the first time the surveyors might become aware of a calibration problem might be in the registration process, which is something we're coming to in the next session, where we'll be dealing with the processing. But at the preparation and fieldwork stage, yeah, obviously we want to get that set up right, because your problems become embedded. And in fact, I would say in terms of metric survey, just generally, all the other sort of data that we do in the condition survey, including costing and so on, errors that are embedded in the metric survey before they've even left the office to carry out the survey will become magnified and more difficult to correct the further you get into the process, until eventually one day you're on site. If somebody comes up to you then and says, sorry, I can't get this right, and you start to do your error trace and you find out that it's just been there all along and hasn't been picked up through any of the QA and error control processes, that's like the nightmare scenario that we don't like to get to that point. That's then an insurance job at that point. So Kira, are you ready to roll again? We've got another section. Let's do it.
Yeah, let's dive into photogrammetry. So our next process of creating a digital twin is to form the realistic 3D model created by photogrammetry. Photogrammetry is the science and technology of obtaining 3D information about physical objects and the environment throughout the process of recording, measuring, and interpreting photographic images. Let's look at the history and how we've developed to the technologies we use today. The concept of photogrammetry was introduced in the 19th century with aerial photography as early as 1860. The term photogrammetry was coined by Albert Meydenbauer in 1867. In the 1900s, stereophotogrammetry was developed for 3D mapping, and the first significant use in mapping and surveying was occurred. Between 1910 and 1940, aerial photography was extensively used in the military, and advancements in mapping technologies for precise targeting were developed. Post-war, technological advancements allowed for introduction of digital methods and early integrations with computers for better accuracy. The present day is showing that digital cameras, LIDAR, and UAVs are revolutionising the field, and modern software tools are enabling high accurate 3D modelling and mapping. Prior to the timeline just shown, back in the 17th century, a man named Johan Zahn took an interest in the science of sight through the human eyes. Johan Zahn was a German priest, optician, and inventor who made significant contributions to the field of optics, astronomy, and mechanics. Zahn's work focused on optics and telescopes, not directly on photogrammetry. However, his contributions to optics helped advance measurement technologies. High-quality lenses and precise optical instruments became essential for accurate photography, which later played a key role in photogrammetry, especially in aerial surveys and 3D imaging. The idea of stereoscopic vision, seen with both eyes, was also important. Stereophotogrammetry uses overlapping photos from different angles to create 3D models, similar to how our eyes work together to perceive depth. Photogrammetry is essentially the method of capturing images from multiple different angles and perspectives, which are then processed and combined to form a 3D visual model. This technique enables the creation of highly accurate and detailed three-dimensional representations of real-world objects, terrain, or structures, often used for mapping, surveying, and modelling applications. Images can be captured using a variety of methods, depending on the specific needs of the project and the accessibility of the target area. Aerial photography with drones, handheld camera photography, or high-level photography with a camera-mounted pole. Historic England provide a webinar discussing remote inspections with drone, and you can check this out free of charge in their training section, and we'll send a link out to this in the group. So drone photography. Drones have become an essential tool in the survey industry, particularly for capturing detailed data of heritage buildings, where traditional surveying methods may be difficult, costly, or time-consuming. By using drones for photogrammetry, surveyors can quickly and accurately gather high-resolution images, creating 3D models and maps of historically significant structures without compromising their integrity. Drone-based photogrammetry utilises UAVs, which is short for unmanned aerial vehicles, equipped with high-resolution cameras to capture detailed images of terrain and objects from above. These images are then processed using photogrammetry software to generate accurate 3D models, maps, and topographic data. This technology has revolutionised the surveying industry by offering a more efficient, cost-effective, and precise method of capturing aerial data. Drone photography for photogrammetry has a wide range of applications, including land surveying, construction planning, agriculture, environmental monitoring, archaeological site mapping, and heritage digital twins. Drone photography has become an invaluable tool in photogrammetry, particularly in the fields that require detailed, accurate, and efficient data collection. Terrestrial photography. This is the photography from ground level opposed to needing a drone. Photographs can be taken from the ground using handheld cameras. This method is often used when access to the object or the area is easy and doesn't require special equipment. For hard-to-reach areas, such as the tops of buildings or deep crevices, a pole-mounted camera can be used. This allows a photographer to reach higher or more difficult positions without the need for ladders or scaffolding. Once these images are captured, they're processed using photogrammetry software. The software identifies common points in the images, matches them across different angles, and then reconstructs the 3D surface by triangulating the spatial positions of these points. This allows for the creation of highly detailed 3D models, topographic maps, and other visualizations. So adding control to drone-based surveys. So as well as using a point cloud to control a photogrammetry model, size and scale, we can use ground control, spoken about in the first section, for large mapping areas of land. In drone-based photogrammetry, adding control to mapping missions is a crucial step for improving the accuracy and precision of the captured data, especially when creating 3D models, maps, or conducting surveys over large areas. Control points, also known as ground control points, GCPs, play a key role in this process by serving as reference markers that help to georeference the drone images, showing that the 3D model or map created aligns correctly with real-world coordinates. So what are GCPs? Ground control points are specific, easily identifiable points on the ground with known geographic coordinates, longitude, latitude, and elevation. These points are marked with high visibility markers, which could be targets, flags, or just special coloured paint that is easy to detect from the air. Why are GCPs important? When a drone captures images for photogrammetry, the software can process the data and create a 3D model. However, without the GCPs, the model might lack proper georeferencing, meaning it could be misaligned or scaled incorrectly. GCPs help to ensure the model or the map corresponds accurately to real-world coordinates. And how are they used? So during the mapping mission, the drone captures images of the terrain with specific focus on the control points. After the flight, the coordinates of the GCPs are manually input into the photogrammetry software, allowing it to correct any distortion and align the model with actual geographic coordinates. GCPs also help to correct for any camera tilt, lens distortion, or flight inaccuracies. So the video is now zooming on a GCP. If you can see that, there's like a blue cross in the center of the screen, and that's what the software is looking for, because the center of each cross has its own georeference point. So as well as needing expensive software for photogrammetry, it can also be a really accessible tool. It does have limitations, but there are ways that you can test this out at home. So why not try the photogrammetry out for yourself? Polycam is an app that you can download initially for free to trial the process of photogrammetry from home. All you need to do is download the Polycam app using the QR code on the screen now, pick an object at home, follow the app's guided steps to scan and create a 3D model, and then explore, edit, and share your creations with the group. I'm excited to see what you managed to get done. Our key benefit takeaways for photogrammetry are its high accuracy, generating precise 3D models and measurements from 2D images, options for cost-effective data capture by using standard handheld cameras, reducing the need for expensive equipment like drones, versatility across applications throughout a range of industries. It's scalable for large or small projects, captures both large-scale environments like cities and small objects like artifacts. Rich visual outputs produce photorealistic textures for enhanced visualization, and it allows for remote and safe accessibility, enabling data collection in hazardous or hard-to-reach areas using drones. Its integration with digital twins can be seamless, and it can be integrated into BIM and other platforms. We will discuss BIM models and all these other platforms in next week's session. So as well as the three main aspects of creating a digital twin, there are so many other methods of data capture available in the surveying industry. Some focus more on visualization, whilst others focus more on their accuracy. 360 photography is a way to capture a spherical view of a scene, allowing users to experience an environment interactively without needing to visit themselves. Using specialised cameras or rigs, photographers take images that are later stitched together to create immersive panoramic views. These photos are often used in virtual tours, marketing and educational resources. As a company, we've utilised 360 photography for projects like virtual town tours, safety induction guides to be completed before site visits, and educational tools for learning. Have a think about how you could utilise a 360 tour to enhance an experience within your industry. Another technique would be to use remote access surveying equipment. Remote access surveying techniques are transforming how we approach challenging environments. Tools like Spot the Dog, which are equipped with laser scanners and cameras, allowing them to navigate hazardous areas autonomously. Similarly, buggies with mounted laser scanners excel in constrained spaces like underground tunnels and unsafe structures, capturing precise data without putting surveyors at risk. These techniques enhance safety, boost efficiency, and ensure high-quality data collection, even in the most challenging conditions. Just like mounting a laser scanner to a remote buggy, you can do this to a car. When a LIDAR unit is mounted to a moving platform, this can also be known as mobile mapping. Its key features are high-speed data collection, flexibility across platforms, and real-time processing, making it a great alternative for some aspects. So our key benefit takeaways for alternative data capture. Much like the benefits of all the surveying techniques we've covered, the alternative data capture methods can be very useful in the right field of work. It can enhance accessibility tools like Spot the Dog and buggy-mounted LIDAR scanners, which excel in environments that are hazardous, constrained, or inaccessible for humans. The improved safety reduces risk to personnel by allowing remote operation in dangerous areas such as tunnels, mines, or industrial sites. Its increased efficiency, automated and mobile platforms enable faster data collection compared to traditional methods, saving time on complex projects. Versatility is suitable for various environments from rugged outdoor sites to narrow indoor spaces, making them adaptable to diverse project needs. And it's a future-proof technology. The integration of robotics and remote control platforms represent the next step in surveying and capture innovation. So to summarise our session today, digital models allow us to bring the projects to life in the virtual world. The benefits are clear, they enhance accuracy and help us visualise designs in great detail. They also improve collaboration between teams, reducing errors during the construction phase, and ultimately save time and money. We've learnt about the wide range of applications digital models can be applied to. They're used in building design, infrastructure projects, site analysis, and even heritage restoration, bringing new life to historic structures. Looking ahead, the potential is huge. With advancements like AI integration and digital twins, we can monitor projects in real time and make better decisions. These models also support sustainability by helping us optimise resources and reduce time on site. As you can see, digital models are a game changer in shaping the way we design and build. It would be great to see you all chatting in the WhatsApp group over the next week leading up to our next session. Feel free to share if you've already used any of these data capture techniques, which ones you prefer and which ones you'd like to explore further through training. And if you're new to all this, we'd love to hear which aspects caught your interest and most how we can help you begin your journey in the surveying industry. Don't hesitate to tag me in your messages. I'd be happy to answer any questions. I'm looking forward to chatting with you all. So next week we're going to be exploring how the collected data is then processed and transformed into deliverable outputs for various applications. So I'll now pass you back over to Linda.
One of the questions I was going to ask you is about the beautiful model, one of my favourite buildings, Liverpool Anglican Cathedral. How long did it take to do the survey, the field work for that?
So the Liverpool model was a digital twin, so it's a combination of survey control, laser scanning and photogrammetry. So for the survey control, it takes a day on site to get round a building of that size, making sure everything's accurate and you close in your traverse loop. And then you've got another day, or even possibly with two people, laser scanning around the outside of a cathedral, making sure that you are, again, creating a loop around the building which will register together. Whereas the photogrammetry consisted of multiple visits due to the detail that's captured. You have to capture every small element on the cathedral in smaller from every angle. So it was a combination of ground-based photography, pole photography, as well as using the drone to capture all the high, couldn't reach areas. And that is the main purpose of the model. So for the architect, Mike Darwell, it worked with all his feasibility studies for issuing all repair work. You could see the model up close and all the details which needed restoration work for elements that you just cannot physically reach on site.
It's interesting, isn't it? Two things jump out of that in terms of how much work is now done by the machines. You know, like you say, the calibration of your photogrammetric images. I can remember that was something years ago when about rectified photography and using these images in that very traditional way of reverse engineering back to flat ortho elevation. Whereas now the machines are linking up, like you say, they're spotting for those target points and they can stitch it all together. Are just unbelievable, the processing power of that. So that's one big thing. And the other thing that the machines are doing, which is really making things a lot faster, is that hybridization between the laser scans and the photogrammetry. So if you go back to my decade-old example of Blackpool Winter Gardens that we talked about in the plenary session, the actual laser scans, the survey work, the traverse, I think even the traverse took about a week, whereas you're able to like get around. I don't know whether the cathedral is it's a simpler building in some ways in terms of footprint, but you were able to get around that, as you say, like in a day. And that's the thing for me, is how the actual site time is so condensed now. Even back in 2019, we were using UAVs a lot less and using pole cameras, and as you say, getting scaffolding out and trying to take images that way. And now the image creation is just so quick. So the field work overall, I'm getting that you probably did about 15 or 20 man days of field work then for that survey of the cathedral. And I think
external, possibly less. Obviously the internal was, because it's a full digital twin, we've fully laser scanned the internal as well, including all the roof spaces and everything like that. So it was an extensive survey internally. But when you're just saying then about how the technology has kind of come on, so the owners of the business, Tom and Chris, they tell me stories about how they used to laser scan, and they used to set off the laser scanner and it used to take 2 hours to do one laser scan, whereas now you can do a black and white laser scan in 27 seconds. So that's how quickly the technology has improved.
Yes. And which in a way is making it more accessible. Because obviously time is money.
Cheaper, yeah.
So we would have had really big clients with really big buildings, really big repair needs or whatever, coming and asking us to help them. Whereas now, and I think we're on the cusp of this is almost like an everyday type approach, especially because the quality of the data and the usability of the models now is so good that it's almost a question of not why would you do it, is why wouldn't you do it? You know, that the traditional techniques now feel more costly and less accurate, and they don't have, as you say, that future proofing of saying when we can come back and do them again. Sorry, I'm just downloading to you now. Another thing that came out in the presentation was when you showed, I think it was the Google car going around doing the Google Maps thing. And when we did the question, we said, who's using these digital models every day? And 50% of people said, nah, not so much. Actually, we already are. all of us. I mean, everybody's using Google Maps. And I know as a surveying tool for safety, when we do our risk assessments, before we go out and we do any field work, the first thing we do is we jump on Google Maps. We see where we're going to park, where's the welfare, what's the neighbourhood like, are we going to get up to the building, what kit do we need with us? All that part of the risk assessment is done using these free to use digital models. So they're out there and they're great. So are there any hands up? Have we got any questions coming? We had a question in the chat room from Brahim. You want to know about ground control points in documenting projects. And Richard has quite rightly said we'll try and cover that off for you next week in a bit more detail. We've got a question from Trevor. Trevor, you want to ask about the weather? Where's Trevor?
Yes, the weather is a big factor. Yeah, all external work. So regarding laser scanning, the rain can affect external laser scanning, but we don't seem to have that many issues or constraints with that. It's something that we can usually work around, whether we scan internally first, and then when we get a break in the weather, we jump outside. Photogrammetry, the wind can be an issue. So drones have limitations on what wind speeds they can work in, but like, for example, 2 weeks ago when we had that crazy windstorm, we wouldn't even send a laser scanner out in that because it's just not worth it. If it gets blown over, it's just not worth the money to wait a day. So yeah, the weather is a big factor.
Oh, and rain and
Great,
visibility.
thank you.
Yeah. Do you go outdoors much then, Trevor? Is that your major constraint?
Not in that weather, no. No, I think as surveyors, we've just got to earn a living, so got to go when you got to go.
Yeah, we like
find an indoor job.
Yeah, we love the field work. But I know that we did something recently with Christians, which was some structural monitoring, and the temperatures, as you know, dipped down very cold. I think we got to -13 at one point. And because we were doing very fine calibration measurements, that actually just the natural thermal movement of the structure would have given us a perverse set of baseline measures. So it's something to always have in mind, is those environmental conditions. We're measuring something that changes, albeit very gradually. We want to measure change, but obviously this is the thing about having the datum and having a steady set of measures to work from. What's coming up, Kira?
So we're going to chat about how the data that we've just spoke about collecting is then processed and transformed into actionable deliverables. So it's one of the benefits of a surveying company already covering these costs. So they have all the softwares available. Some processes are really easily and accessible, whereas other processes can take up to a week to create the deliverables. But then for the client, they are effectively their final outcome, which helps them in so many different ways, like how you use your ortho images, Linda, for marking up. We do a lot of work for companies where we need to, our 2D drawings need to have stone for stone elements, so the stone for stones can be marked up, and that in turn is like a link of all the laser scanning, the photogrammetry, and all the process data coming together to create a final package.
I couldn't be more grateful. Thanks so much. Bye-bye, everybody.
Bye.